Hello, this is Dr. Strickland. In this video, we will begin our investigation of the reactions of carbonyl compounds with hydrogen nucleophiles. Take a minute to read through these student learning objectives. These are the things you should be able to do by the end of this video so that you're ready for the things we will do together in class. Now, if you look down this page, you'll see that we're going to talk about the interaction of aldehydes and ketones, acyl chlorides, and esters with hydrogen nucleophiles. So like with the carbon nucleophiles, we're going to start with aldehydes and ketones, and then we're going to talk some about how carboxylic acid derivatives interact with hydride ions. Now, with aldehydes and ketones, we're talking about sodium borohydride and lithium aluminum hydride. This is sodium borohydride. This is lithium aluminum hydride. Both of them are classified as hydride reducing agents or hydride transfer reagents. Now, sodium borohydride is less reactive than lithium aluminum hydride. So any carbonyl compound that's reactive enough to be reduced by this guy can also be reduced by that guy. And that is true for ketones and aldehydes. So I've used this in our general reaction pattern, but it's a ketone, but just know that it could also represent an aldehyde if R prime were a hydrogen, because it does all the same things. So the first thing I want you to do is take this general reaction pattern and use it and show me what the product of this reaction would be. And then come on back. All right, welcome back. So the product here would involve the transformation of this ketone to an alcohol. And with ketones and aldehydes, I can tell you that an aldehyde will be transformed into a primary alcohol, and a ketone will be transformed every time into a secondary alcohol. And this can be very handy to know when you're trying to decide where to begin in a synthesis problem. So let's take a look at the mechanism. And I'm going to stick with the general structures here. So it can be either a ketone or an aldehyde. Sodium borohydride is a salt. And the borohydride anion, which has a negative charge, looks like this. I know it has a -1 charge because sodium has a +1 charge. So the electrons of this bond and the hydrogen are the nucleophile. So we get to a tetrahedral intermediate that looks like this. And there's the hydrogen that's been added. And then in step 2, we're going to protonate it. Now in practice, sometimes when you use sodium borohydride, sometimes an alcohol is used as the proton donating agent. So you will see some of that in your problems. And if R prime is a hydrogen, then this is a primary alcohol. And if R prime is an alkyl portion, then this is a secondary alcohol. And this is, if you want to keep up with annotations, this is step 1 and this is step 2. Now with acyl chlorides, we find that they are reduced either by sodium borohydride or by this guy here, which is lithium tri-T-butoxy aluminum hydride. It's just a fancy hydride transfer reagent. And again, you know, if it will react with sodium borohydride, it would also react with lithium aluminum hydride. So I've given you 2 general reaction patterns here because they get you to different places. You start with an acyl chloride in both cases, but this one takes you to a primary alcohol, and this one takes you to an aldehyde. So it gives you some options. So if my acyl chloride looked like this, and I used the lithium tri-T-butoxy aluminum hydride, what would I make? Pause the video and draw the structure. Okay, welcome back. So the carbon that's involved is that one. And we know from this general reaction pattern on the right that it's going to an aldehyde. So all of this alkyl portion stays the same. It really doesn't make any difference if it's complicated or simple. And because hydrogens attached to carbons don't have to show in aldehydes, you can leave it like that. Or if it makes you feel better, you can put the hydrogen on. Sometimes it looks more balanced to me like that, and that's fine. With esters, we have a similar situation, but esters are a lot less reactive than acyl chlorides. Remember, acyl chlorides are more reactive than aldehydes and ketones. Esters are less reactive than those two kinds of compounds, and that should be on the first page of your notes. So we do have to use lithium aluminum hydride if we're going to use something similar to this one and get to the alcohol. To get to the aldehyde, we're going to use this guy here, which is diisobutyl aluminum hydride, which sometimes is abbreviated DIBAL or DIBAL-H. You may see that in your homework. But the same kind of choices, one way to get you to a primary alcohol, one way to get you to an aldehyde. All right, so in this case, I see I have an error because sodium borohydride won't do. Let's change that. Needs to be lithium aluminum hydride. All right, but in this case, well, I want you to do this. Pause the video, draw the structure, and come on back. All right, welcome back. So this is going to take us down to the primary alcohol. So the carbonyl carbon is the star of the show. There's that carbon, ends up with an OH. And you can draw two bonds to hydrogens, or you can draw it like this. As long as two hydrogens and an oxygen and this phenyl group end up attached to that carbon, there are a variety of ways to draw it. So let's take a look at the mechanism. So this will remind you of the mechanism that we did involving a Grignard reagent with an ester. Because we're going to get nucleophilic attack twice. So this in the lithium aluminum hydride, this is the aluminum hydride anion, and boron and boron and aluminum are both in group 3A. So if they have 4 covalent bonds, they have to have a negative charge. And if you want to calculate it out for the two of them, you can convince yourself that that has to be so. But same kind of thing, transfer of one of these hydrogens with its electrons to the carbonyl carbon gets you to here. That gives us a tetrahedral intermediate with a negative charge on the oxygen. We're in a very basic medium. So just like with the mechanism we saw with the Grignard, this tetrahedral intermediate is going to eject the least basic piece because it can. And that gets us to this aldehyde, which is very reactive towards incoming hydride ions. And so we're going to get attacked a second time. Now, in fact, these hydride ions with either lithium or boron can transfer more than one hydride ion apiece, but I'm just going to draw it with 2 fresh ones, and we won't deal with that at the moment. All right, the negatively charged oxygen is here. Here's the first hydrogen that was added and the second hydrogen that was added. And then it will sit right here and wait for you until you add something that will protonate that alkoxide ion, that negatively charged oxygen. And I drew it as hydronium ions this time. Negative charge on the oxygen. Could use that pair of electrons to accept the proton. And in a protonation step, remember, this is the transfer of the hydrogen atom without the electrons. With this nucleophilic attack, the hydrogen is transferred with its electrons. So that's really different. All right, so the product looks like this. All right, so please answer the question at the end of the video and then come on back.